Hi, we are Carlos Sánchez Ramírez and José Antonio Torres Millán. We are going to present Chapter 4, Network Access. We are going to start with physical layer protocols. In order to be a network communication, must be established a physical connection to a local network, Ethernet switch, or wireless access point. Often, switch devices and WAPs are two separate dedicated devices. However, there are also devices that offer both wired and wireless connectivity. These devices are called ISRs, Integrated Service Routers, that have a switching component with multiple ports, allowing multiple devices to be connected to the local area network, LAN, using cables. These devices also have WAP that allows wireless devices to connect. Network interface card connect a device to the network. Ethernet NICs are used for a wired connection, where wireless local area network NICs are used for wireless. An end-user device may include one or both types of NICs. Wireless device will experience degradation in performance based on its distance to a wireless access point. The further the device is from the access point, the weaker the wireless signal it receives. This can mean less bandwidth or no wireless connection at all. On the other hand, a wired connection will not degrade in performance, however, is extremely limited in movement and generally requires a static positioning. Purpose of the physical layer. The OSI physical layer provides the media to transport the bits that make up a data link layer. The process that the data undergoes from a source node to a destination node is the user data is segmented by the transport layer, placed into packets by the network layer, and further encapsulated as frames by the data link layer. Then, the physical layer encodes the frames and creates the electrical, optical, or radio wave signals that represent the bits in each frame. These signals are then sent on the media one at a time. The destination node physical layer retrieves these individual signals from the media, restores them to their bit representations, and passes the bits up to the data link layer as a complete frame. Physical layer media. There are three basic types. Copper cable. The signals are patterns of electrical pulses. Fiber optical cable. The signals are patterns of light. Wireless. The signals are patterns of microwave transmissions. We can see all these patterns in the image. The protocols and operations of the upper OSI layers are application, presentation, session, transport, network, and data link that are designed by the Internet Engineering Task Force. The physical layer consists of electronic circuitry, media, and connectors developed by engineers, so it's appropriate that the standards governing this hardware are defined by the relevant electrical and communication engineering organizations. Some of these organizations are International Organization for Standardization, ISO, Telecommunication Industry Association, TIA, International Telecommunication Union, ETU, American National Standards Institute, INSI, Institute of Electrical and Electronics Engineers, IEEE. Also, there are often regional cabling standard groups, such as Canadian Standard Association, European Committee for Electronical Standardization, and Japanese Standards Association. In the next table, we can see a lot of networking standards developed by each organization. Fundamental Principles Layer 1 address three functional areas. The physical components are the electronic hardware, devices, media, and other connectors that transmit and carry the signals to represent the bits. Encoding. Encoding or line encoding is a method of converting a stream of data bits into a predefined code. In the case of networking, encoding is a pattern of voltage or current used to represent bits, the zeros and ones. Signaling. The physical layer must generate the electrical, optical, or wireless signal that represent the 1 and 0 on the media. This is similar to how Morse code is used for communication. Signals can be transmitted in one of two ways, asynchronous and synchronous. In the table, we can see the media, physical component, frame encoding technique, and signaling method. Bandwidth. Different physical media support the transfer of bits at different speeds. Data transfer is usually discussed in terms of bandwidth and throughput. Measure of the transfer of bits across the media over a given period of time. The practical bandwidth of a network is determined by a combination of factors, the properties of the physical media, and the technologies chosen for the signaling and detecting network signals. The factors that influence the throughput are the amount of traffic, the type of traffic, and the latency created by the number of network devices encountered between source and destination. Network media. Network use copper media because it's cheap, easy to install, and has low resistance to electrical current. The drawback is that the copper is limited by distance and signal interference. The electromagnetic interference or radio frequency interference are signals that can distort and corrupt the data signals being carried by copper media. On the other hand, there is crosstalk. Crosstalk is a disturbance caused by the electric or magnetic fields of a signal on one wire to the signal in an adjacent wire. In the image, we can see the interference of the different types of signal. There are three main types of copper media used in networking: unshielded twisted pair, shielded twisted pair, and coaxial. Are used to interconnect nodes on a LAN and infrastructure devices such as switches, routers, and wireless access points. Unshielded twisted pair cabling is the most common networking media. UTP cabling terminates with RJ45 connectors. Is used for interconnecting network hosts with intermediate networking devices, such as switches and routers. Consists of 4 pairs of color-coded wires that have been twisted together. The twisting of wires helps protect against signal interference from other wires. Shielded twisted pair provides better noise protection than UTP cabling. STP uses 4 pairs of wires, each wrapped in a foil shield, which are then wrapped in an overall metallic braid or foil. Coaxial cable gets its name from the fact that there are 2 conductors that share the same axis. In the coaxial cable, there is a copper conductor used to transmit the electronic signals. The copper conductor is surrounded by a layer of flexible plastic insulation. The insulating material is surrounded in a woven copper braid or metallic foil that acts as the second wire in the circuit. UTP cabling. UTP cable does not use shielding to counter the effects of EMI and RFI. Instead, cable can limit the negative effect of crosstalk by cancellation. Consists that when 2 wires in an electrical circuit are placed close together, their magnetic fields are the exact opposite of each other. Therefore, the 2 magnetic fields cancel each other out and also cancel out any outside. The other way is varying the number of twists per wire pair. AEEE rates UTP cabling according to their ability to its performance and are placed into categories depending on their bandwidth rate. Cable Category 3, used for voice communication. Cable Category 5, used for data transmission. Cat5 supports 100 megabits per second. The Cat5e supports 1000 megabits per second. Cable Category 6, used for data transmission. An added separator is between each pair of wires, allowing each to function at higher speeds. Supports 1000 megabits per second to 10 gigabits per second. UTP cable is usually terminated with an specified RJ45 connector. This connector is used for a range of physical layer specifications. The RJ45 connector is the main component, crimped at the end of the cable, The socket is the female component in the network device, wall, cubicle partition, outlet, or patch panel. The UTP plugs and UTP sockets are shown in the image. Different situations may require UTP cables to be wired according to different wiring conventions. The most common type of networking cable, it is commonly used to interconnect a host to a switch and switch to a router, that is, Ethernet straight through. The Ethernet crossover is an uncommon cable used to interconnect similar devices together. It is used to connect a switch to a switch, a host to a host, or a router to a router. And the rollover, a Cisco proprietary cable used to connect to a router or switch console port. In the image, we can see the UTP cable type, related standards, and typical application of these cables. Fiber optic cable permits the transmission of data over longer distance and higher bandwidths than any other networking media. Unlike copper wires, fiber optic cable can transmit signals with less attenuation and is completely immune to EMI and RFI. It is being used in 4 types of industry. Enterprise networks. Fiber is used for backbone cabling application and interconnecting infrastructure devices. FTTH and access networks. Fiber to the home is used to provide always-on broadband services to home and small business. Long-haul networks. Service providers use whole terrestrial optical fiber networks to connect countries and cities. Networks typically range from a few dozen to a few thousand kilometers and use up 10 gigabits per second based systems. Submarine networks. Special fiber cables are used to provide reliable high-speed, high-capacity solutions capable of surviving in harsh undersea environments. The core consists of pure glass and is the part of the fiber where light is carried. Cladding, the glass that surrounds the core and acts as a mirror. The light pulses propagate down the core while the cladding reflects the light pulses. Jacket, typically a PVC jacket that protects the core and cladding. It may also include strengthened materials and a buffer coating, whose purpose is to protect the glass from the scratches. Types of fiber media. Single mode. A small core, less dispersion, suited for long-distance application. Uses lasers as the light source. Commonly used with campus backbones for distance of several thousands of meters. Multimode. Larger core than single-mode cable. Allows greater dispersion and therefore loss of signal. Suited for long-distance application, but shorter than single-mode. Uses LEDs as the light source. Commonly used with lengths or distance of a couple hundred meters within a campus network. Fiber connectors differ in size and methods of mechanical coupling. About 70 connector types are in use today. Because light can only travel in one direction over optical fiber, 2 fibers are required to support full duplex operation. Optic cable requires special training and equipment. Common types of fiber optic termination and Lysine errors are misalignment. The fiber optic media are not precisely aligned to one another. End gap. The media does not completely touch at the splice or connection. End finish. The media ends are not well polished or dirt is present at the termination. Fiber versus copper. Given that the fibers used in fiber optic media are not electrical conductors, the media is immune to electromagnetic interference. Greater length than copper media. No need of signal regeneration. Wireless media carry electromagnetic signals that represent the binary digits of data communication using radio or microwave frequencies. Media of choice for home networks and gaining in popularity in enterprise networks. Areas of concern. Coverage area. Wireless data communication technologies work well in open environments. However, certain construction materials used in buildings and structures and the local terrain will limit the effective coverage. Interference. Wireless is susceptible to interference and can be disrupted by such common devices as household, cordless phones, some types of fluorescent lights, microwave ovens, and other wireless communications. Security. Wireless communication coverage requires no access to a physical strand of media. Therefore, devices and users who are not authorized for access to the network can gain access to the transmission. Consequently, network security is a major component of wireless network administration. Types of wireless media. The IEEE and telecommunication industry standards for wireless data communications cover both the data link and physical layer. Three common data communication standards that apply to wireless media are Standard IEEE 802.11, Wireless LAN, commonly referred to as Wi-Fi. Standard IEEE 802.15, Wireless Personal Area Network, standard commonly known as Bluetooth. Standard IEEE 802.16, commonly known as interoperability for microwave access, uses a point-to-multipoint topology to provide wireless broadband access. Wireless LAN requires the following network devices. Access point concentrates the wireless signals from users and connects usually through a copper cable to the existing copper-based network infrastructure such as Ethernet. The SNIC adapter provides wireless communication capability to each network host. Wi-Fi standards. In this image, we can appreciate the Wi-Fi standards. The most evolved in speed is the 802.11 AD with 7 gigabits per second.
Now we are going to talk about data link layer protocols. In this layer, it connects the upper layers of communication to the media. Also, it spares them from worrying about the access to the media. It has two specific functions: receive packages from the third layer and store them into frames before going to the physical layer, and control the access of the media and perform error detections. It has two sublayers: the Logic Link Control (LLC) and Media Access Control (MAC). The first one is a bridge between frame and the third layer. This layer is in charge of selecting the correct frame for the media that is being used. A single frame can be created here to travel through different media. In the second one, this one is in charge of managing the access to the media and the amount of data that is being sent and received according to the media used. The MAC, or Media Access Control, gets a frame on and off the media. In other words, they describe the way network devices access network media and transmit diverse frames in different network environments. This allows communications to develop and be established without worrying about media technologies developed for transmission. The steps that are followed for media access are: accept the frame from the medium, de-encapsulate the frame, re-encapsulate the packet into a new frame according to the new medium, and forward the new frame appropriate to the medium of a segment of the physical network. Frames encapsulation. Encapsulating a packet means giving a header and a trailer like a travel diary. We have a header that normally has the addressing data that contains the IP header, transport layer header, and the application data, and the trailer, which contains the error detection. Control information is used for the protocols to function correctly. They give us the answer to the next questions: which nodes are they in communication with each other? When does communication between individual nodes begin and when does it end? Which error occur while the nodes communicate? Which nodes will communicate next? In the frame we have different files. Data travels through the media in forms of zeros and ones and that go through a single stream. Frames is the way to know where does a packet start and where does it end without any other help. This is done by giving specific amounts of bits to each part of the frame. This is called framing. Divisions in the frame fields are: frame start and stop indicator flags, addressing, type, control, data, and error detection. Standards. Data link layer services and specifications go according to multiple standards and protocols according to the media and technologies. They incorporate various layers 1 and 2 services. Engineer organizations establish public open standards and protocols. Communication companies set up proprietary protocols and standards for new technology to take advantage of the market. Data traffic requires techniques and methods to help it flow in order and quickly without causing any losses. They depend on two things, topology and media sharing. In topology, we have how are the nodes connected and view from the data link layer. We have two kinds of topology, physical and logical. In the physical refers to the connections and identifies how end devices and infrastructure devices such as routers, switches, and wireless access points are interconnected. Some of these topologies are point-to-point and start. In the logical topology, refers to how data travels from one node to the next one. It is a virtual connection from one point to another that a data link layer sees when deciding where to send the packages. This topology determines the type of framing and MAC that is going to be used. Media sharing is how the nodes share the media. Some examples are point-to-point or share media. Some physical topologies are the point-to-point, the star, and the full mesh topology. In the point-to-point, we have permanent connection between two endpoints. In the next one, in the hub and spoke topology, we have a connection of a central site to a branch site through point-to-point connections. The full mesh topology is a high-cost topology, since every end device needs to be connected to every other end device. This requires high administrative and physical costs. In the point-to-point physical topology, this does not require too many logical data link protocols. They do not share the media with any other device. In addition, media access control becomes unnecessary. Point-to-point logical topology focuses on the virtual circuit formed between two end devices. It does not matter if there are a series of nodes and intermediary devices between them. This topology determines the media access method used by the data link layer. Communication between nodes can be of two ways, half duplex and full duplex. In the half duplex, both devices send and receive by taking turns. They do not talk simultaneously. In the full duplex, the data link layer assumes that the media is always available for communication. This results in both devices sending and receiving data simultaneously. LAN physical topology. We have a star topology, extended star topology, and bus topology, and ring topology. The star topology have end devices connected to a central intermediary device, while the extended star are various star networks that are interconnected through a bus topology. The bus topology end devices are chained to each other, and there is no need for switches. In the ring topology, end devices are connected to their respective neighbors. This communication is established through tokens that goes from one to another to allow the end device to transmit. This token works like a ticket that allows the end device to communicate or to start transmitting data to the other devices. This packet goes from one to another until it arrives to the correct one. LAN logical topology. There is need for controlling media access, and this is done through two basic media access control methods. Contention-based access. In this method, devices have to fight for the right to transmit in the media. This causes for the media to have various collisions. To help fight the collisions, we have carry-sense media access. This helps the devices to know when to transmit and to only transmit when the media has no other signal from any other end device. However, as the network starts to grow in devices and in distance, the collisions start to happen more frequently. There are two tools to manage contention: carry-sense multiple access with collision detection and carry-sense multiple access with collision avoidance. The first one is a method that detects that if there is anyone transmitting, and if there is anyone transmitting, the device waits for some time to try transmit again. The second one, after checking the media to start transmitting, the device sends a notification of its intention to transmit, usually used in wireless communication. Contention-based access is often used in multiple access logical topology, in which media is shared for a series of end devices. Through this topology, everyone can see the packets that are being sent, however only one device processes the information. The other method is control access, also known as schedule access. In here everyone has a turn to use the media. To ensure the turns, the end device receives a token allowing them to transmit, and once the packet reaches the destination, the token is released. The benefits of having organized traffic and fewer transmission errors is only contradicted against the time used to send data. This means the device has to wait longer for a bigger networks. Data link frame. It is composed by the header, the data, and the trailer. The information in it varies depending on the fragility of the media. The more fragile environment, more control data is needed for a better management of the data. Data link frame. It is composed by the header, the data, and the trailer. The information in it varies depending on the fragility of the media. The more fragile environments, more control data is needed for a better management of the data. The header. For Ethernet there are three fields: a start frame field, source destination address fields, and type field. Other fields may include priority quality of services field that indicates a particular type of communication service for processing. Logical connection control fields. They are used to establish a logical connection between nodes. Physical link control field, used to establish the media link. Flow control field, used to start and stop traffic over the media. Congestion control field indicates congestions in the media. Data link layer provides addressing. In the header frame, it is stored the destination of the packet. Physical address is unique for every device, and thus it can help us locate physically. That is why, as a measure of security, it is only used through local communication. In a WAN, where data travels from one network to another, routers help them interconnect. With it, data has physical address to get to the routers. Routers then de-encapsulate to watch the IP address and send the data to the end device. Trailer. In this part of the frame, an error log is created along the transmission. A transmitting node makes a local summary of the content. This is called Cycle Redundancy Check, CRC. This log is stored into the frame check sequence. When the package arrives its destination, the final node forms a CRC and compare it with the FCS to determine if the file is corrupted or not. Data link protocols. They may vary from network to network, since LANs require protocols to adapt to their fast media technologies, unlike WANs. Some of the more common protocols are Ethernet, point-to-point protocol, and 802.11 wireless. Ethernet. It supports data bandwidths of 10 megabytes per second, 101 giga, or 10 gigas. Ethernet provides an unacknowledged connectionless service over a shared media using CCNA1v5 as the media access methods. It is required to use data link layer address to identify source and destination nodes. This address is the MAC address. As we can see in the image, the frame has 6 types of field for the Ethernet protocols. Point-to-point protocol. Point-to-point protocol uses layers resulting in lower and upper PPP protocols. Each of them form a session in a connection to a node. PPP also allows the two nodes to negotiate options within the PPP sessions. This includes authentication, compression, and multilink. As we can see, we have another 6 fields for the frames used in PPP protocols: the flag, the address, control, protocol, data, and frame check sequence. Wireless protocols. To overcome many obstacles in wireless transmission, many controls are implemented. It is a contention-based system, so it uses data link acknowledgement to know when a packet arrives. If nor the packet nor the acknowledgement is received, data is retransmitted. Other services supported by these protocols are authentication, association, and privacy.